just so that we are on the same page, uh, Snakes and Ladders is a game where two players take turn rolling a die with the goal of reaching the end of the board first. If they land on the base of a ladder, for example, on square 50 here, then they climb up to the top of that ladder, in this case, square 69. However, if they land on the head of a snake, so for example, the little orange one here, square 40, then they will slide from the head of the snake down to its tail, in this case, square number 3. Firstly, so let's build it. Firstly, let's talk about what makes up the game of snakes and ladders. We have all the start and end positions of the snakes and ladders. We have the square that the players are currently positioned on. And then finally, we need to know whose turn it is. If I gave you that information, then chances are very good that you'll be able to recreate a board of the game Snakes and Ladders. So let's talk about the game state. That contains all the little doodads on the screen, which is the Snakes and Ladders. The player's position, in this case, red is on square 29, and blue is on square 36, as well as whose turn it is. Just viewing this, we don't actually know whose turn it is, so we need to store that in somewhere. So it might look a bit like this. So here we have the game state. We have a dictionary of the start and end position of all our snakes and all our ladders. So I think this may not correspond to what you saw exactly, but the concept is still the same. So for example, in my dictionary of snake positions, I have a snake whose head is on square 93, and they'll slide back down to 73. And likewise, and this is just a list of, well, this is just dictionary of all those key value pairs. And likewise, I have the same thing for the ladders. So for example, on square 51, we have a ladder that goes all the way up to square 67. We also have two player 1 and player 2 variables to keep track of where our players are on the board. In this case, I'm instantiating them to 0 because we begin at square 0 because, I don't know, somewhere along the lines, we started counting at 0, not at 1. And then finally, we have a Boolean to keep track of whose turn it is. Here, I've just got a little variable that says, is player's 1 turn? And it's true. So to start up the game, we start off with our dictionary of snakes and ladder positions. We start off with our player 1 and player 2 on square 0. And we start off with player 1, who goes first. Now, what is the core game loop in a game of snakes and ladders? First, we check whether or not the game is over. So if, for example, in this case, it'll be if someone has dropped off the end of the board. We won't implement the, if you need to roll exactly the right number to reach the end square. We'll just say if they reach the end square of 100 or so or more, then they win the game. And if the game is not over, then the current player rolls a die, and then that player then moves that many squares. We then move the player again if they land on a snake or a ladder. Sorry, just give me 2 seconds. Yep. So then we move the player again if they land on the head of a snake or the base of a ladder. And then finally, once that's done, we switch players. So what would that look like in code? Well, it might look a bit like this. So we first check whether or not the game is over and translate it into code. It looks like this. While player 1 is less than max squares and player 2 is less than max squares, then the game continues. Then we store the current player square in a temporary variable because we'll be doing a lot of manipulations on it, and it just makes things a little easier. Then we roll a die. So this line here, we returns back a number, a whole number between 1 and 6. And then we need to move that player that many squares. So we're just going to go current player plus equals dice roll, which gets the current player's position and then adds on the dice roll and then reset and then sets that number back to the variable current player. Now, adding the dice roll to the current player's location, it's only part of the picture. We need to move the player again if they land on a snake or a ladder. So here, we're treating this imperatively. We have two for loops that iterate through the keys of our snakes, which represent the head of the snake. And if we find a match, then we access the value of that key, which represents the base, the tail of that snake. So here we iterate through all the key value pairs inside our snake dictionary. If the base matches where the current player is, then we set the current player's position to the base of a snake, to the tail of a snake. Otherwise, this loop does nothing. And then we repeat the same logic for the list of ladders, which remember, the key was the base of the ladder, and the value was the end of the top of the ladder. So once again, we iterate through all the ladder positions. If the ladder position's base is the same as the current player's position, then we promote them to the top of the ladder. We then need to do a little bit of accounting because remember, all this time we're doing manipulations on our temporary variable current player. And then we really need to assign it back to either player 1 or player 2, depending on whose turn it is. And then finally, we switch whose turn it is. And then adding in a few console logs, I'll show you that it works and that I didn't just make all this up. So here is what we just went through. So we have, max squares, the dictionary of all the snakes, the dictionary of all the ladders, player 1, player 2, whose turn it is, as well as the core game loop, where, we roll the die, we add the die, we handle the snakes, we handle the ladders, and then we print where they ended up and then switch the players. So moment of truth. We'll click this, and if the demo gods are smiling, we should see something. And hooray, if you look down here in the console log, you see that works. You see that the players are rolling die, they're going up ladders. So for example, the player 1 hit a ladder on number 4 and ended up at square 14. And then we see that the core game loop works. And then finally, someone wins the game. In this case, it was player 2 who landed on square 100. It works. However, there's a problem. And that problem is that all the code is jumbled together. And in order to understand what the code is doing, we have to read and understand all of it. It might be okay in a game of snakes and ladders where it's relatively simple, but imagine like a complex web app or I don't know, something more complicated. And this would become quite a burden to have it to read and understand all the code. So let's take a look at an example. Why so much reading? We know, I want you to direct your gaze towards this while loop here. We know that the block inside our while statement is checking whether or not the game is over. However, this code in its current form is not ideal. Why is it not ideal? The reason is because we need to read the entire line and to know about the rules of snakes and ladders to understand what it is doing. And that leads us to our first interesting point about functions. And that is the functions have names. And we can use those names to describe and modularize our code. So we know that the block inside our while statement is checking whether or not the game is over. So instead of having to rely on the reader read all of that and understand it, we can instead extract it out into a function and then give it a meaningful name. So instead of saying while player one less than max blah 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 blah, we chuck all that into a function, and then the function name is game in progress. And then our while loop looks like this. While is game in progress, and it takes in player one and player two's position. In my opinion, I want to ask the question, which is, which one is easier to read? Is it the first line or the third line here? In my opinion, it is much easier to read the bottom line because the name of the function separates out what it does, what it is, away from what it does. We can then repeat the process for the other blocks of our code base. So instead of having to ask like do this line saying current player equals is player one turn, question mark, player one, player two, we just extract that out into a function and call it get player turn. Instead of having to understand math.random, math.for, blah, 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 and then understand the intricacies of how math.random works, we just call the function roll dice. Roll dice, die, one or the other. And then likewise, we do the same instead of going through the array or through the dictionary of snake positions. We just call it, handle snakes, and likewise handle ladders. And then finally, we have a function here that says update game state. So we have split out the logic for determining whose turn it is, rolling the dice, handling their snakes and ladders, and also to update the game state. Extracting out blocks of code and giving them names now leads to our core game loop looking like this. Let's go through this together. While is game in progress, we get the player's turn. We then roll the dice. We then add the dice roll to the current player. We handle the snakes. We handle the ladders. And then we tell the just console log out where they landed up. And then finally, we update the game state. Let's do a quick comparison from our first version with our latest version. Remember, the first version had all of this, and you need to read it all to understand what it was doing. The second version, the detail is hidden within functions, and if you read just the core game loop, it looks like this. I personally find the version on the right much easier to read, and all we are doing is separating out blocks of code into a function and calling that function, and that function has a name. That leads us to our first point in the functional paradigm, which is we can use named functions to modularize our code. We can give the functions meaningful names that abstract away from what you want your code to do from what the code actually does. So this is a small step. We have started our first journey along our journey down the functional paradigm. And all we're doing is treating functions as named procedures. All right, so we've been learning a lot so far, and I want to take a short mental break to talk about another topic. So if you're seated, please feel free to stand up, stretch, and whatever you need to do. This will only take a minute, and I will tell you about my dog. So I have a little floover, and his name is Pixel. He's a 3-year-old Japanese Spitz. He enjoys going to doggy daycare and is a good fluffy boy. So here we have a picture of him with a snazzy little bow tie. Here we collected all his fluff one time and then recreated his pose with 2 blueberries. So yeah, you can't even tell the difference between the two. And then here he is drooling and just loving life, looking at a rainbow. Not quite sure what's going on in that little brain of his, but he looks very happy. Anyway, thank you for listening to my story about my dog. And we're back. To recap, we had just finished splitting out our game of snakes and ladders into separate named procedures, and we saw the benefits of just doing that and how easy it is to read the code just doing that. However, we need to understand a bit more about what the words in functional paradigm means. So let me explain a little bit more. When functional programmers use the word function, they usually mean a very specific type of function that is more akin to a mathematical function. So when functional programmers talk about functions, functions come in two flavors. They are either pure or impure. And when functional programmers talk about functions, they generally refer to pure functions. Pure functions have two properties. They always return the same output given the same input, and they have no side effects. The first point is similar to how a function in mathematics, so for example, y equals 2x plus 1, where we're graphing a line that goes from the left to the right, up, and to the right. If you give the same value x to that formula, to that mathematical function, you will end up with the same value y, regardless of how many times you feed in the value x. And this is how we want to treat our, uh, our computer function, programming functions. We want them to always return the same output given the same input. And the second point about having no side effects means that executing the code will not modify anything outside of the function itself. So for example, if you run this, you don't expect, I don't know, your printer to start printing out like 3 sheets of black paper or something like that. Uh, that and the reason why you don't want that is because if it did that, it makes it very, very hard to reason about that function. It makes it hard to reason about imperial functions. First, let's start off with an example of an impure function. Here we have a function from our previous example. Remember before the break, we were talking about this is the function that checks whether or not the game is in progress. However, we can see that it is an impure function because we can't describe the output completely from its inputs, as there is a reliance on this external variable max squares. So for example, if we run this and both players are on square 50 and 60 and max squares was 100, then it would return back, yes, the game is in progress. But if they were on the same squares 50 and, did I say 60? Sure, 60, but max squares was 30, then the game would not be in progress. So as you can see, just reading this function and the inputs and outputs, you can't completely describe the output. So therefore, it is an impure function. However, it's a fairly easy change in this circumstance to turn it into a pure function. All we need to do is pass in the max squares in as part of the inputs. And now our function here is a pure one because it is completely described by its inputs. You can get the output. So if you provide the same inputs, then you're always going to get the same outputs. But why is this important? It is because pure functions are completely described by its inputs and outputs. And this allows you to stop thinking about the details of the function and instead think in terms of inputs out outputs. So for example, f1 is a function, and you don't need to, if it was a pure function, you don't need to know about the details. You just know that it is a function that turns squares into circles. So let's relate this back to code and take a look at this function here at the top, isEven. IsEven is a function that takes in a number and then checks whether or not it is even. It is a pure function because it is completely defined by its inputs and outputs and has no side effects. We can see that in this case, it is a function that takes in a number and returns back a Boolean because it checks whether or not the number is divisible by 2 and returns back true if it's divisible by 2 and false otherwise. I'm using squares and circles here to emphasize that when we start using pure functions, we can start thinking about the types that go in and out of our functions, the types being the type of the inputs and the type of the outputs. Which leads us to our second step down the functional paradigm. When we start using pure functions, we unlock the ability to start thinking about our code as a transformation of types. So pure functions are not constrained by just working on numbers and booleans. We can invent our own types to feed into our own functions. So for example, consider what defines the state in a game of snakes and ladders. I would argue that the following would be a pretty good start, where we have all the snake locations, we have all the ladder locations, we have the player locations, we also store whose turn it is, as well as how big the board is. So if we combine all of these slices of our game state into an object, then it might look a bit like this. In this case, this we have player one, who's player one, player two starting off on square zero. Player one's turn is true because they start first. We have the dictionary of all the snakes. We have a dictionary of all the ladders, and we also store a variable. We also store what the size of the board is. So this is just cramming all of the stuff earlier into a single object, and we now call the shape of this object state. Part of thinking in the functional paradigm is to manage state effectively. Now that we have described our state, how do we get to our next state? So the game of snakes and ladders is all about going from one board state. You throw a die, and then you get a new state. So in a game of snakes and ladders, a dice roll determines going from one state to the next. If we want to use pure functions to describe our game loop, it might look a bit like this. We want to create a new function called getNextState that takes in two arguments, one to represent the dice roll, and the other is to represent the current state. And then we would then return back, we would do some manipulations on the current state, taking into account the dice roll, and then we'll get back the same type that represents the next state. Let's talk concretely and look at some code. So I've left the image down on the bottom here, so so we can all see the similarities between the code and the diagram. So we take in the dice roll, and we also take in the initial state here as an input. We then extract out the stuff that we want out of the current state, and then we return back the same shape of object as the next state. Here, we're spreading over the initial state, which just destructures it and repeats what's inside the initial state. However, we manipulate, depending on whose turn it is, the location of player one. If it's player's one turn, then we add the dice roll to the player. We handle the ladders, we handle the snakes. And likewise, if it's player's two turn, then we do the same to player two. And then finally, we change whose turn it is. But what about the game loop? It might look a bit like this. To run a game, we start from the existing state. We then check if the game is over. Otherwise, we run the game again with the next state, including the dice roll. And then this would recursively run until the game is over, in which case it will finally print out the game over message. Let's compare the core game loop from our previous version to our current version. Note that in our latest version 3, we have actually stopped talking about the snakes and ladders. We could be talking about any board game that where the next state can be determined by a dice roll, because all that detail is abstracted inside the getNextState function. And the idea of decomposing, so we've actually solved all board games which can be deterministically which can be determined going from one state to the next state with a dice roll. So it includes like the airplane game, for example. The idea of decomposing a problem into a question of what inputs you need to get from one state to the next is a powerful one inside the functional programmer's tool chest. And this leads us even further down the functional paradigm, where our snakes and ladders game is no longer thought of in terms of its individual parts, but holistically as a series of state transitions moving from one state to the next according to inputs. So we have transcended just making solutions for the game of snakes and ladders and set her a framework that solves all games that get from one state to the next with a dice roll. In summary, we have written the game Snakes and Ladders several times, each time following the functional paradigm a bit more. We started off without using any functions, and although it worked, it led to code that needed the reader to really read and understand every single line, and it was a bit hard to reason about. We then moved a little further down the functional paradigm journey, where we split out the blocks of functionality in our code into separate functions with names and saw the benefits from that. After that, we realized that our individually named procedures had external dependencies, making them hard to reason about in isolation. And then we realized the benefits of using pure functions over impure functions. And then finally, instead of viewing snakes and ladders in detail, we instead abstracted the entire game into a series of state transitions. And although this was a bit of a contrived example, I want to stress that I want to stress back, go back to the slide about how the functional paradigm was a scale. It doesn't matter if you stop at functions as named procedures, for example, because you get benefits from each. You can choose where to stop along the functional paradigm and get the benefits that you want from that point in the journey. And I hope this entices you to learn a little bit more about the functional program paradigm and start your journey solving problems using a more functional approach. And if you want to hear a bit more about state, then I believe I will be presenting next week on React and State SPS. Any questions?
I feel like all the questions that are going to come at you would be in relation to Pixel right now, William.
I'll happily talk about my dog.
Very, very cute. Thank you so much. Is anybody got any questions that they'd like to put in the chat?
Oh, yep. One sec.
Hello.
I think I have to pay the dog tax.
Oh, that is super cute. Love
that. Give me 2 seconds. There we go. How many pics? This is
oh
Pixel.
My goodness. Okay. I love the guest appearance. That's brilliant. All right. Well, if that's all we've got this evening, would you be able to share your slides, and I'll pop the actual recording in Slack as well for everybody.
Yep. Should I share it to you via Slack?
Yep. Okay. Brilliant.
Yep.
Thank you so much for your time on a Monday evening.
Yep. Thank you all.
And we look forward to your webinar next week, where we'll have no technical issues whatsoever.
Yep. Thank you. Enjoy the rest of the evening.
Lovely.
Thank you so much, William.